and Amu for hosting. So I'm Jeremy, I'm an engineer at Google and I work on Kubeflow, and today I'm going to talk to you about how you go about building ML products with Kubeflow. So basically, okay, hang on. It says it's waiting for the host to start the meetup. So. Your screen. Good. Unmute me. All right, we're just trying to get the Zoom conference going. I don't think it would share audio through my computer, would it? Because I don't have my microphone plugged in. Or... Okay, so all right, sorry for that interruption. Hopefully that's all working now. So the agenda basically is I'll provide some background on Kubeflow, you know, what it is, the rationale for it, and then we're going to go through an end-to-end example, walking through how you'd build a relatively simple ML product today with Kubeflow and how that helps you. And then finally, we'll summarize with just a brief summary and some roadmap. So ML is kind of ubiquitous these days. It's all the rage, you know, thanks to a lot of products that have really transformed the way we do things, like self-driving cars, AlphaGo, and Google Translate. And there's also lots of ML products from non-Google companies as well. So, you know, there's a perception today that if you're building ML products, that, you know, the ML product looks like this, where most of the code and infrastructure for that product is about ML, right? So you think about ML, you think very complicated neural networks, a lot of complicated algorithms, a lot of really complicated math. And then around this, you know, core algorithm, you have a bunch of supporting services. You know, you've got some services to do things like data collection. You've got some configuration management for your infrastructure where you're going to be running the product. You've got some feature extraction tooling. You've got some machine resource management tooling. And of course, you actually have to serve your models and deploy them. And then that brings up a whole set of monitoring challenges. So I think there's a real perception that, you know, from where you spend your time and energy is all about the ML code. And what we've learned at Google is that really the ML becomes a very small piece of this, and that you end up spending most of your time and energy around these other supporting services, right? Because what ends up happening is you end up having a distributed system, and once you have a distributed system that's running in production, that brings with it a whole bunch of DevOps challenges. Trying to talk to me through Zoom. I muted them. Sorry if you're on the Zoom. I don't know how to make that work. So this is what we've learned at Google. You know, operating large-scale ML systems in production. So we've learned that there's lots of DevOps challenges, and that's what we're trying to solve, right? So what we've learned and seen over the past couple of years is that, you know, what's really good at solving these DevOps challenges is containers and Kubernetes. And so with Kubeflow, what we're trying to do is make it possible to build portable ML products using Kubernetes, right? So by portable, we want to build ML products that can run anywhere, whether that's in the cloud or in your on-prem data centers, or running locally on your laptop as part of your dev test cycle. So what is Kubeflow specifically? First and foremost, we are a community, and that community is very broad. So we include data scientists, ML researchers, software engineers, product managers, And the reason that what brings us together as a community is that we're all trying to build a ML platform on top of Kubernetes. And the reason that we're coming together as a community to do this is because I think there's a growing realization that building an ML platform is a really big problem, and it's really quite difficult to tackle alone. And this is sort of a lesson that we've taken from the Kubernetes community. So if you go back 2 to 4 years ago, everybody was building different orchestration platforms for containers. Everybody was trying to sort of build their own orchestration platform by themselves. And really what we've seen is that, Kubernetes got going, and I think one, in part because they built an active and energetic community, and people realized, found ways to build their own products and companies on top of that. And so what we're trying to do is we're trying to build a Kubernetes native platform for ML. And so what we mean by that is a couple things. First and foremost, we want to run wherever Kubernetes runs. So we're using Kubernetes as our portability layer. So Kubernetes provides a lot of high-level abstractions and patterns for building distributed systems. It also runs pretty much everywhere in terms of on-prem, on your laptop, in the cloud. So if we build a Kubernetes native platform, then we should be very portable and be able to move that platform wherever Kubernetes runs. And as part of that, we're trying to take advantage of Kubernetes patterns and abstractions to manage ML tasks. So as an example, in Kubernetes, there's a concept of a custom resource, which allows you to manage distributed systems, whether that's etcd or rollouts for your servers. And so we've taken advantage of this customizability to build custom resources for managing ML tasks like distributed training and then model deployment. And then as part of being Kubernetes native, we're seeing a lot of patterns and conventions emerge in the Kubernetes community. As an example, it's all about microservices and managing infrastructure declaratively. So we're trying to take advantage of those patterns and bake them into our platform so that it feels very native and natural to people familiar with Kubernetes. And then finally, specifically, what we provide is we provide KSNet packages. That's a configuration management tool for managing infrastructure declaratively and deploying all the different microservices and packages you need as part of your ML platform. And one of our goals is to support multiple frameworks. So we want to support not just TensorFlow, but we also are adding support for PyTorch, as well as other frameworks like scikit-learn and XGBoost. And then finally, one of the things that we want to do is we want to provide end-to-end solutions illustrating how ML products get built on Kubeflow. And that's one of the things I'm going to be demonstrating today. So let's walk through an end-to-end example. So typically, you would start by deploying Kubeflow, and you can deploy Kubeflow either on-premise or in cloud. And so this is an example. Let me see if I can play this. This is a video that was a tool that was built by Canonical, which is one of our partners. And they've built this little wizard that walks you through basically setting up your Kubeflow deployment, and then it will automatically sort of provision a Kubernetes cluster and then deploy Kubernetes as you need, as needed, and then configure and deploy Kubeflow on top of that. And so these just filling out various options. And then we're building similar tools to run on other platforms like GCP. Okay, so if you're trying to solve an ML problem at a high level, this is a schematic of what it might look like, that workflow might look like. So first you would identify a problem, then you would do a little bit of ad hoc experimentation exploration to see whether you actually can solve this problem using machine learning. Then you'd probably try to train a model. Then you'd try to deploy that model. And then you would have to operate that model and system in production. And this tends to be an iterative process. So after you've deployed the model, you'll go back and do some more experimentations and use those experiments to refine your model. So let's start with an example problem. So one of the example problems that we can think of is if you're managing an open source project, so you have a project in GitHub, you often run into this problem where you have GitHub issues with uninformative titles. So a typical example is a user might file a bug, and they don't know what's going on or what's wrong, so they file a generic title like X doesn't work. So after you go through and debug the issue and help them out, you identify what the problem is, you might want to go back and update the title to make it easier to find this issue in the future and maintain the health and hygiene of your repository. So as a specific example, this is one of the issues that we had in our Kubeflow repository. So a user filed an issue with some setting problems. A new guy needs a little help, which isn't very descriptive. After we went through that and triaged it, we updated the title with a more specific title based on the error message. So this is what you'd really like to do, is keep these titles up to date, but that entails a lot of toil. And so this is an area that would be ripe for automation by using machine learning to see whether you can automatically generate titles based on issues so that you can automatically update them. So let's go through a demo. So if you were starting, typically the first step is you want to do some exploration and experimentation. So typically for that, you would want to use a tool like Jupyter. So that's your very friendly data scientist environment, so that you can do some interactive data analysis to explore data and see whether there's signal there. So as part of Kubeflow, we deploy Jupyter Hub on Kubernetes. So Jupyter Hub is a multi-user notebook server, and this makes it really easy to provision for your different data scientists' notebooks. And you can take advantage of Kubernetes to do resource management. So you can take advantage of auto-scaling to automatically provision more nodes or more resources in your cluster if you have more users. And you can also provision resources like GPUs and more RAM to the notebooks as needed. So in this case, I have a notebook, and this is a notebook that was built by Hemal Hussain at GitHub. So he was the data scientist who came up with this example and published a blog post about it. And so if we go through the notebook, he basically starts out with downloading some data, and then he samples the data a little bit because it's too big to process sort of interactively in his notebook. He does some initial exploration. So here he's just printing out what that data looks like so you can get a sense of what features are in the data. And so in this case, it's just he's reading from a BigQuery table where they have different, each row corresponds to a GitHub issue. So they have columns like issue URL, issue title, etc. He then does some pre-processing. So in this particular case, he's building a text model. So he does some generic, some standard natural language processing, like building a vocab. And that's what he's doing here. Here he's using, I think, using parts of Keras to do this standard vocab generation. And also he's tokenizing the text. And then down here, he's actually defining his neural network to generate titles. And you can see down here, he's defining the model architecture. And if we actually print out, we can actually print out a graph here of what the model looks like. And then down here, he trains the model. Nothing particularly spectacular there. And then finally, after he trains the model, he can do some examples, compute some evaluation metrics on the holdout data set. And then in this case, he can actually put some examples into it. So he's put in an example here, which is the body of the issue. And then this is the actual title that gets generated. So this is great. He went through and did an initial experimentation and exploration and proved that he could build a model. But as part of doing that, he only trained on a small set of data. And so to build a higher quality model, he probably would want to scale out and run for a really long time using more resources. In particular, he might want to run distributed training. So for that, with Kubeflow, we provide, as I said, a custom resource for doing distributed training on Kubernetes. And so one of the challenges of doing distributed training with TensorFlow is that you end up having to manage multiple processes. So you have a parameter server, which is basically a distributed key value store for your parameters. You then have the workers that are actually computing the gradient updates. And then you have your master, which is doing all the coordination of these gradient updates and applying them to the parameters. And so you have to manage all these processes. And so you can do it natively yourself, but we've gone ahead and built a custom resource to do this. And so the way that Kubernetes works, I don't know how familiar people are with Kubernetes, but you have a declarative spec. And in that declarative spec, you define what you want to run. So in this case, we have a spec. And then in the template for the spec, we can specify all the different TensorFlow processes. So in this case, we're not running distributed, so we have a single replica. And then down here, we specify the replica type, which is what function this replica is going to be performing in our job. So in this case, this is the master. And then in the pod template spec, we can specify the Docker image that contains our code, and then the actual command that we want to run. And so that's how we can go ahead and launch that, and then that can run asynchronously, unlike our notebook environment, which is sort of an interactive environment. And so we can launch a whole bunch of these jobs and use a lot of resources to train really high-quality models. And then switching back, so if you're training your models with TensorFlow, you probably want to use TensorBoard to visualize your results. Not sure why it's having oh, there it goes. So we make it really easy with Kubeflow to deploy TensorBoard, so you can see the results and quality of your model. And then we wire that TensorBoard up through Ingress and reverse proxy so that you can access it from outside your Kubernetes cluster. Once you have the your model trained, then you actually have to go and deploy it. And so that we provide integration with a bunch of different model servers. So you can use TensorFlow serving, or you can use Seldon. And Seldon provides, let me show it. So Seldon provides a custom resource to manage rolling out models, machine learning models into production. So in this case, we've gone ahead and created a Seldon deployment to deploy our model. And so this is what that spec looks like. So just as with our TF job, we have our declarative YAML spec that specifies what we want to roll out. And in this case, we specify a Docker image, which is the Docker image for the model that we built from the trained Keras model. And so we can go roll that out into production. And then we also, in this case, might want to have a front-end UI that provides a web app. So this is the web app that we sort of built. So in this case, we entered a GitHub issue. You can then click Generate Title. It would go and fetch the body of that GitHub issue, then it feeds that into the title, into the model, and then it generates the title, which in this case is fairly accurate for what the actual problem was. So switching back. So to summarize, this is what our final system ended up looking like, right? So we started off by doing some experimentation and exploration to see whether we could actually solve this problem. And so for that, we went ahead and deployed Jupyter Hub so that we could give our data scientists a useful environment. Once we were done doing some experimentation and exploration, we had to train at scale. So we had to go and deploy our TensorFlow job controller so we could run TensorFlow jobs. To support our TensorFlow jobs, we had to go and launch TensorBoard so we could see what our models were doing. Once we were done training, we had to go and deploy these models. So for that, we took advantage of the Seldon controller. So we had to go and deploy that, and then use that to deploy our actual models, along with our web front end, which is actually providing a web app. Since we have multiple services running in production, we want to take advantage of something like Istio to provide monitoring and telemetry data. And now, since we have multiple microservices that are web services, we need a way to access them. So for that, we're taking advantage of Ambassador, which is a reverse proxy. And then we want to be able to access this from outside the cluster, so we have to connect this to a load balancer. And then since we are accessing it from the outside world, we need to secure it. So we need to connect it with external authentication so we can only let trusted users in. So even though our system and problem is relatively simple compared to some of the other ML examples out there, we still quickly end up in this case where we're running a distributed system with multiple microservices, and we need to keep those up and healthy in order to build successful ML products. So here's our roadmap. So we released our first 0.1 release in April, and that included some core components. So we include Argo, which is a Kubernetes native workflow scheduler. We have Jupyter Hub. We have our initial release of TF Job, which is our TensorFlow job controller. We're integrating with Seldon, which provides a CRD for model deployments. And then we also provide support for TensorFlow serving. We're releasing our 0.2 release at the end of this month. So we have some new components coming. So we have Katib, which is a hyperparameter tuning system. We're adding support for PyTorch. We're adding support for batch inference and Horvath. That's an MPI framework for TensorFlow from Uber. And then we have some other improvements like a click-to-deploy solution. And then we're targeting our 1.0 release, hopefully by the end of the year, at KubeCon in December. So to summarize, if you're building ML products, you end up with distributed systems that come with them, that bring with them significant DevOps challenges. And with Kubeflow, we're trying to solve those problems by taking advantage of Kubernetes. So that's my spiel. Be happy to answer any questions. I think we have a couple minutes left.
I have a mic here, so if you have questions, feel free to.
Jeremy, thanks for a great talk. And I got a question for you. So how does it compare to the ML Flow, which is just announced at Spark Summit?
I don't really know. I'm not too familiar with ML Flow, so I can't comment. I don't really know what they're doing. So.
Thanks for the talk. So you're in a corporate environment. Let's say if you want to use this, you want to integrate with your corporate authentication, for example, how does this work for Kubeflow?
So we're looking to Kubernetes to provide a lot of those integrations. It's still one of the areas that's underdeveloped in Kubernetes, but eventually we'd like, there's some integration like with Kubernetes with like your existing IAM systems like LDAP and your other OAuth providers. There's some additional work to map that into the permissions inside your Kubernetes cluster, which is called RBAC. So we're trying to get that functionality in Kubernetes because that's really where it belongs. And then with the Kubeflow community, we're trying to take advantage of that to define sort of sensible policies by default. So, you have a data scientist, user role that has permissions that don't allow them to do things like open up the cluster to the external world because they probably shouldn't be allowed to do that.
Another question is, does it come with a storage solution? Let's say for distributed training, most of the time you probably need a distributed file system.
Yeah, so we're trying to find, Kubernetes is not a storage system, but they provide abstractions in the form of their volume management system that allows you to interact with different types of file systems, right? So you can create a volume for like an NFS share, and then you can attach those volumes to your pods so that you can read and write from them as part of your TensorFlow jobs. And then you can also speak directly to object stores like GCS or S3 or even HDFS. And then the problem becomes, how do you take advantage of Kubernetes patterns to inject appropriate credentials into your pods? And so that's the kinds of problems that we're trying to solve with Kubeflow and make really seamless for data scientists and ML research. Any other questions? All right, if not, thank you very much.